The decibel is a logarithmic unit used to express the ratio of two values of a physical quantity, often power or intensity. One of these values is often a standard reference value, in which case the decibel is used to express the level of the other value relative to this reference. The number of decibels is 10 times the logarithm to base 10 of the ratio of two power quantities, or of the ratio of the squares of two field amplitude quantities. 1 decibel is 1/10 of 1 bell, named in honor of Alexander Graham Bell. However, the bell is seldom used. The definition of the decibel is based on the measurement of power in telephony of the early 20th century in the Bell system in the United States. Today, the unit is used for a wide variety of measurements in science and engineering, most prominently in acoustics, electronics, and control theory. In electronics, the gains of amplifiers, attenuation of signals, and signal-to-noise ratios are often expressed in decibels. The decibel confers a number of advantages, such as the ability to conveniently represent very large or small numbers, and the ability to carry out multiplication of ratios by simple addition and subtraction. By contrast, use of the decibel complicates operations of addition and subtraction. A change in power by a factor of 10 corresponds to a 10 decibels change in level. At the half-power point, an audio circuit or an antenna exhibits an attenuation of 3 decibels. A change in voltage by a factor of 10 results in a change in power by a factor of 100, which corresponds to a 20 decibels change in level. A change in voltage ratio by a factor of 2 approximately corresponds to a 6.02 decibels change in level. The decibel symbol is often qualified with a suffix that indicates the reference quantity that has been used or some other property of the quantity being measured. For example, dBm indicates a reference power of 1 milliwatt, while dBu is referenced to approximately 0.775 volts RMS. In the International System of Quantities, the decibel is defined as a unit of measurement for quantities of type level or level difference, which are defined as the logarithm of the ratio of power or field type quantities. History. The decibel originates from methods used to quantify signal loss in telegraph and telephone circuits. The unit for loss was originally miles of standard cable. 1 MSc corresponded to the loss of power over a 1-mile length of standard telephone cable at a frequency of 5,000 radians per second, and matched closely the smallest attenuation detectable to the average listener. The standard telephone cable implied was a cable having uniformly distributed resistance of 88 ohms per loop mile and uniformly distributed shunt capacitance of 0.054 microfarad per mile. In 1924, Bell Telephone Laboratories received favorable response to a new unit definition among members of the International Advisory Committee on Long-Distance Telephony in Europe and replaced the MSc with the transmission unit. 1/2 was defined such that the number of TUS was 10 times the base 10 logarithm of the ratio of measured power to a reference power level. The definition was conveniently chosen such that 1/2 approximated 1 MSc. Specifically, 1 MSc was 1.0562. In 1928, the Bell system renamed the 2 into the decibel, being 1/10 of a newly defined unit for the base 10 logarithm of the power ratio. It was named the Bell, in honor of the telecommunications pioneer Alexander Graham Bell. The Bell is seldom used, as the decibel was the proposed working unit. The naming and early definition of the decibel is described in the NBS Standards Yearbook of 1931. Since the earliest days of the telephone, the need for a unit in which to measure the transmission efficiency of telephone facilities has been recognized. The introduction of cable in 1896 afforded a stable basis for a convenient unit, and the mile of standard cable came into general use shortly thereafter. This unit was employed up to 1923, when a new unit was adopted as being more suitable for modern telephone work. The new transmission unit is widely used among the foreign telephone organizations, and recently it was termed the decibel, at the suggestion of the International Advisory Committee on Long-Distance Telephony. The decibel may be defined by the statement that two amounts of power differ by 1 decibel when they are in the ratio of 100.1, and any two amounts of power differ by n decibels when they are in the ratio of 10n. The number of transmission units expressing the ratio of any two powers is therefore 10 times the common logarithm of that ratio. This method of designating the gain or loss of power in telephone circuits permits direct addition or subtraction of the units expressing the efficiency of different parts of the circuit. In April 2003, the International Committee for Weights and Measures considered a recommendation for the inclusion of the decibel in the international system of units, but decided against the proposal. However, the decibel is recognized by other international bodies such as the International Electrotechnical Commission and International Organization for Standardization. The IEC permits the use of the decibel with field quantities as well as power, and this recommendation is followed by many national standards bodies, such as NIST, which justifies the use of the decibel for voltage ratios. The term field quantity is deprecated by ISO 80000-1, which favors root power. In spite of their widespread use, suffixes are not recognized by the IEC or ISO. Definition: the ISO standard 80000-3-2006 defines the following quantities. The decibel is 1/10 of the bell. 1B equals 10 decibels. The bell is lane NEPAs. 1B equals lane NP equals lane NP. The NEPA is the change in the level of a field quantity when the field quantity changes by a factor of E, that is 1 NEPA equals lane equals 1 ratio of 101/20. Although permissible, the bell is rarely used with other SI unit prefixes than deci. It is preferred to use hundredths of a decibel rather than millibels. The method of expressing a ratio as a level in decibels depends on whether the measured property is a power quantity or a field quantity. See field, power, and root power quantities for details. Power quantities. When referring to measurements of power quantities, a ratio can be expressed as a level in decibels by evaluating 10 times the base 10 logarithm of the ratio of the measured quantity to reference value. Thus, the ratio of P to P0 is represented by LP, that ratio expressed in decibels, which is calculated using the formula. The base 10 logarithm of the ratio of the two power levels is the number of bells. The number of decibels is 10 times the number of bells. P and P0 must measure the same type of quantity, and have the same units before calculating the ratio. If P equals P0 in the above equation, then LP equals 0. If P is greater than P0, then LP is positive. If P is less than P0, then LP is negative. Rearranging the above equation gives the following formula for P in terms of P0 and LP. Field quantities and root power quantities. When referring to measurements of field quantities, it is usual to consider the ratio of the squares of F and F0. This is because in most applications power is proportional to the square of field, and it is desirable for the 2 decibel formulations to give the same result in such typical cases. Thus, the following definition is used. The formula may be rearranged to give similarly. In electrical circuits, dissipated power is typically proportional to the square of voltage or current when the impedance is held constant. Taking voltage as an example, this leads to the equation, where V is the voltage being measured, V0 is a specified reference voltage, and GdB is the power gain expressed in decibels. A similar formula holds for current. The term root power quantity is introduced by ISO standard 80000-1 to 2009 as a substitute of field quantity. The term field quantity is deprecated by that standard conversions since logarithm differences measured in these units are used to represent power ratios and field ratios. The values of the ratios represented by each unit are also included in the table. Examples: all of these examples yield dimensionless answers in dB because they are relative ratios expressed in decibels. The unit dBW is often used to denote a ratio for which the reference is 1 W, and similarly dBm for a 1 mW reference point. Calculating the ratio of 1 kW to 1 W in decibels yields the ratio of square root 1000 V 31.62 V to 1 V in decibels is 1 kilowatt, 1 W, illustrating the consequence from the definitions above that GdB has the same value, 30, regardless of whether it is obtained from powers or from amplitudes, provided that in the specific system being considered power ratios are equal to amplitude ratios squared. The ratio of 1 milliwatt to 10 W in decibels is obtained with the formula. The power ratio corresponding to a 3 decibels change in level is given by a change in power ratio by a factor of 10 corresponds to a change in level of 10 decibels. A change in power ratio by a factor of 2 is approximately a change of 3 decibels. More precisely, the factor is 103/10, or 1.9953, about 0.24% different from exactly 2. Similarly, an increase of 3 decibels implies an increase in voltage by a factor of approximately square root 2, or about 1.41. An increase of 6 decibels corresponds to approximately 4 times the power and twice the voltage, and so on. In exact terms, the power ratio is 106/10, or about 3.9811, a relative error of about 0.5%. Properties. The decibel has the following properties. The logarithmic scale nature of the decibel means that a very large range of ratios can be represented by a convenient number, in a similar manner to scientific notation. This allows one to clearly visualize huge changes of some quantity. See Bode plot and semi-log plot. For example, 120 decibels SPL may be clearer than, a trillion times more intense than the threshold of hearing. Level values in decibels can be added instead of multiplying the underlying power values, which means that the overall gain of a multi-component system, such as a series of amplifier stages, can be calculated by summing the gains in decibels of the individual components, rather than multiply the amplification factors, that is, log equals log plus log plus log. Practically, this means that, armed only with the knowledge that 1 decibel is approximately 26% power gain, 3 decibels is approximately 2 times power gain. For example, a system consists of 3 amplifiers in series, with gains of 10 decibels, 8 decibels, and 7 decibels respectively, for a total gain of 25 decibels. Broken into combinations of 10, 3, and 1 decibel. This is 25 decibels equals 10 decibels plus 10 decibels plus 3 decibels plus 1 decibel plus 1 decibel with an input of 1 watt. The output is approximately 1 W x 10 x 10 by 2 by 1.26 by 1.26 equals 317.5 W. Calculated exactly, the output is 1 W by 1025/10 equals 316.2 W. The approximate value has an error of only plus 0.4% with respect to the actual value, which is negligible given the precision of the values supplied and the accuracy of most measurement instrumentation. Advantages and disadvantages. Supporting arguments. According to Michka, the advantage of using a logarithmic measure is that in a transmission chain, there are many elements concatenated, and each has its own gain or attenuation. To obtain the total addition of decibel values is much more convenient than multiplication of the individual factors. The human perception of the intensity of sound and light approximates the logarithm of intensity rather than a linear relationship, making the dB scale a useful measure. Decibels are still the commonly used units to express ratios in a number of fields, even when the original meaning of the term is obscured. Decibels are the traditional way of expressing gain or margin in such diverse disciplines as control theory, antenna and radio frequency transmission theory, and even assessment of nuclear hardness. Criticism. Various published articles have criticized the unit decibel as having shortcomings that hinder its understanding and use. According to its critics, the decibel creates confusion, obscures reasoning, is more related to the era of slide rules than to modern digital processing, are cumbersome and difficult to interpret. Representing the equivalent of 0 watts is not possible, causing problems in conversions. Hickling concludes, decibels are a useless affectation, which is impeding the development of noise control as an engineering discipline. A common source of confusion in using the decibel occurs when deciding about the use of 10*log or 20*log. In the original definition, it was a power measurement, and is employed in that context. The formulation 10*log should be used, as deci means 1/10. The user must be clear whether the quantity expressed is power or amplitude. It is useful to consider how power or energy is expressed, e.g., current resistance, 0.5 velocity mass. If the formulation is a square function of the variable, then 20*log is the correct expression. In simple ratios without obvious power or energy contexts, such as damage ratios in nuclear hardness assessments, the 20*log is commonly used. Quantities in decibels are not necessarily additive, thus being of unacceptable form for use in dimensional analysis. For the same reason that humans excel at additive operation over multiplication, decibels are awkward in inherently additive operations. If two machines each individually produce a sound pressure level of, say, 90 decibels at a certain point, then when both are operating together we should expect the combined sound pressure level to increase to 93 decibels. But certainly not to 180 decibels. Suppose that the noise from a machine is measured and found to be 87 dBA, but where the machine is switched off, the background noise alone is measured as 83 dBA. The machine noise level may be obtained by subtracting the 83 dBA background noise from the combined level of 87 dBA, i.e., 84.8 dBA. In order to find a representative value of the sound level in a room, a number of measurements are taken at different positions within the room, and an average value is calculated. Compare the logarithmic and arithmetic averages of 70 decibels and 90 decibels. Logarithmic average equals 87 decibels. Arithmetic average equals 80 decibels. Users. Acoustics. The decibel is commonly used in acoustics as a unit of sound pressure level. The reference pressure in air is set at the typical threshold of perception of an average human, and there are common comparisons used to illustrate different levels of sound pressure. Sound pressure is a field quantity, therefore the field version of the unit definition is used, where pref is the standard reference sound pressure of 20 micropascals in air or 1 micropascal in water. The human ear has a large dynamic range in sound reception. The ratio of the sound intensity that causes permanent damage during short exposure to the quietest sound that the ear can hear is greater than or equal to 1 trillion. Such large measurement ranges are conveniently expressed in logarithmic scale. The base 10 logarithm of 1012 is 12, which is expressed as a sound pressure level of 120 decibels re 20 micropascals. Since the human ear is not equally sensitive to all sound frequencies, noise levels at maximum human sensitivity, somewhere between 2 and 4 kHz, are factored more heavily into some measurements using frequency weighting. Electronics. In electronics, the decibel is often used to express power or amplitude ratios, in preference to arithmetic ratios or percentages. One advantage is that the total decibel gain of a series of components can be calculated simply by summing the decibel gains of the individual components. Similarly, in telecommunications, decibels denote signal gain or loss from a transmitter to a receiver through some medium using a link budget. The decibel unit can also be combined with a suffix to create an absolute unit of electric power. For example, it can be combined with m for milliwatt to produce the dBm. 0 dBm is the level corresponding to 1 milliwatt, and 1 dBm is 1 decibel greater. In professional audio specifications, a popular unit is the dBu. The dBu is a root mean square measurement of voltage that uses as its reference approximately 0.775 vrms. Chosen for historical reasons, the reference value is the voltage level which delivers 1 milliwatt of power in a 600 ohm resistor, which used to be the standard reference impedance in telephone circuits. Optics. In an optical link, if a known amount of optical power, in dBm, is launched into a fiber, and the losses, in dB, of each component are known, the overall link loss may be quickly calculated by addition and subtraction of decibel quantities. In spectrometry and optics, the blocking unit used to measure optical density is equivalent to -1 Video and digital imaging. In connection with video and digital image sensors, decibels generally represent ratios of video voltages or digitized light levels, using 20 log of the ratio, even when the represented optical power is directly proportional to the voltage or level, not to its square, as in a CCD imager where response voltage is linear in intensity. Thus, a camera signal-to-noise ratio or dynamic range of 40 decibels represents a power ratio of 100 to 1 between signal power and noise power, not 10,000 to 1. Sometimes the 20 log ratio definition is applied to electron counts or photon counts directly, which are proportional to intensity without the need to consider whether the voltage response is linear. However, as mentioned above, the 10 log intensity convention prevails more generally in physical optics, including fiber optics. So the terminology can become murky between the conventions of digital photographic technology and physics. Most commonly, quantities called dynamic range or signal-to-noise would be specified in 20 log dBs. But in related contexts the term should be interpreted cautiously, as confusion of the two units can result in very large misunderstandings of the value. Photographers typically use an alternative base 2 log unit, the f-stop, to describe light intensity or dynamic range.